Let me start a show algorithm. Let me just briefly recall you some basic arithmetics. So the first thing that is important for RSA or for RSA modulus, so it's that z over nz is not an integral domain, so you have a zero divisor. So for instance, for n equal 15, so 5 and 3 are zero divisor. And so divided by nz, in fact, is not a field, and z over nz star is not as easy as z over p star. So because there is a lot of elements that are not invertible. So for instance, here, so the notation, sorry. Sorry. Yes. Yes, so this set, in fact, is a multiplicative group. So all element, and this is called the multiplicative group of invertible element. Okay, so in this set, all elements are invertible, and in fact, it's not a too complicated group. In fact, it contains a few elements. For instance, for z 15z star, in fact, it contains all elements that are not, so that the GCD between the element and 15 is 1. Okay? So you have all x between 1 and 15, such that the GCD of x and 15 is equal to 1. And so the set here contains 1. So you have 2, you don't have 3, you have 4, you don't have 5, you don't have 6 because of 3, 7, 8, so you don't have 9, neither 10, 11, you don't have 12, 13, and 14. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8 elements in this set. And the number of elements in this set is a well-known function that is called the Euler-Toten function. So usually it's written phi of n, and it's exactly the cardinal of this set. Okay, so here, in fact, when n is can be factorized as p times q, so phi of n is very easy. It's pi minus 1 times q minus 1. Okay? So here you can check that the formula is correct because we have p equal to 3 and q equal to 5. And so here we have 2 and 4. And so the number of elements is 8. Okay? So we have exactly what Euler predict. And in fact, so the main difference between the group of this morning and now is that this group is not cyclic. Okay, so you don't have, it cannot be generated by just one element. You need at least 2 elements to generate it. Okay? However, you can take one element and look at the subgroup generated by this element. Okay, and if you take A, for instance, and you look at all the power of A, so 1, A squared, etc. So at some point, in fact, you will go back to 1. Okay, so this is not the little Fermat theorem, it's an extension of this theorem, which is called the Euler theorem. And exactly it says this. Okay, and in fact, the subgroup generated by A is in fact a subgroup of this larger group. And so, according to Lagrange theorem, we know that the cardinal of this subgroup divide, in fact, the cardinal of this group. Okay, so this is what I called here. So the R, which is what is the order of A, in fact, is the number of elements in the subgroup generated by A, divide, in fact, the cardinal of this subgroup, of this group. Okay? And in fact, we will be interested in fact, look at this function. Okay, so we will take, in fact, a random element A, and we will look at, in fact, all the power of A. Okay, and this will define, in fact, a periodic function. And our goal is to find this function, because I will explain to you that as soon as you have found, in fact, an even order for some element, you will be with high probability, you will be able, in fact, to factorize. Okay? So the first thing is that if A is of even order, and it will be the case with probability 1/2, so I will not go into the detail even if you have some question at some point. But in fact, here you can see that we are exactly the same situation as this morning, because here I can always write A to the R by A to the R divided by 2 square. Okay? And if I took this one on the other side, so I will take, in fact, a difference between 2 square, because A is some square also, and then I will get this equation. Okay, so I get this equation only if the order of A is even, but with probability 1/2 it will be the case. So if it's not the case, you will have to find another element. Okay? Okay, so what is also important is that, in fact, here we have 2 different terms, and so we need to know, in fact, so this equation says that n divide, in fact, this product. Okay, but it can be the case that A divide this term or this term. Okay, so we have to look at this situation, and for instance, for the first case, so this is not the case. So the reason is very easy, is because R, in fact, is the smallest integer that satisfies this equation. Okay? And if here we have A to the power R divided by 2 minus 1, which is equal to 0 model, that means that R over 2 is another order, and so this is not possible. However, it's possible that n divide this term, okay? And in fact, we can show that this is not the case with high probability. Okay, so this is maybe not too complicated to show this. So the idea is that now we have, we have in this situation, in fact, we know that here, in fact, we have what is called a trivial root of unity, because minus 1 is a trivial root of unity. Yes, square root of unity. And in fact, if you want to see how many square we have, so the idea is the following. So if you have mod p, so we can look at this equation. And mod p, this equation has only 2 roots, plus or minus 1, because p is a prime and we are in a field. And if you are in a field, so each equation like this, you cannot have more than the degree here. Okay? And so there is only 2 solutions which are plus or minus 1. Okay? And this is also the case mod q. So we only have 2 solutions. Here, okay? But if you are interested in the number of solutions of this equation, so mod n, so the number of solutions is higher, okay? Why? Because if you have if this equation is true, that means that you also have x squared equal to 1 mod p and x squared equal to 1 mod q. Okay, since p and q divide n, if this equation is true modulo n, is also true modulo p and modulo q. Okay, and so here you have, in fact, 2 solutions for this value, plus or minus 1 mod p. And for this equation, you have plus or minus 1 mod q. Okay? So before going into the detail, so let me just remind you something that is very useful. It's called the CRT theorem that says that, in fact, you have some isomorphism between this and this. Okay? And what does it mean in particular? It means that if we look at, for instance, this case, so we can write, in fact, all elements in this set into a pair of elements, mod P and mod Q. Okay, so you can take 1, and 1 is, so 1, mod 15, and you wrote it mod 3 and mod 5. Okay, so here I have 1, I computed mod 3, so it's 1, and if I computed mod 5, it will be 1. Okay, I can take 2, it's also the same here, and now I can take, for instance, 4, and I will associate it 4 mod 3, it will be 1, and 4 mod 5 will be 5. Take 7. So here 7 mod 3 is 1, and mod 5 it will be 3. Yes, 8. You can do the same. Okay, so here you have 2, and you have 3, etc., etc. Okay, so this is a real mapping, and you can go from left to right and from right to left. Okay, so from left to right, it's very easy, but the other direction is a little bit more complicated, but not too much. Okay, and maybe I can write 14. So 14, it can be written as a 2 and 4. Okay. So now, I will show you that we have many different roots of unity, and we have 4. So for instance, if we are interested in this equation mod 15, in fact, we have always 2 solutions. So plus and minus 1 are trivial solutions for this. Okay? And the trivial solution, so 14 is in fact minus 1 is 14, okay? But, so, for instance, x squared equal 1 mod 3, and x squared equal 1 mod 5. Okay, so here the solution will be, in fact, plus or minus 1, but plus or minus 1 mod 3 is 1 and 2, okay? And here, plus and minus 1, in this case, it will be 1 and 4. Okay? So in fact, you see that we have 4 solutions. Either we have 1, 1, 2, 1, 1, 4, and 2, 4. Okay? Half of this solution will be, in fact, trivial square root. So here, it's equal to 1. So we go from this to this. 2 and 4, it will be 14, but this is equal to minus 1. And we have 2 other solutions, which is 2 and 1. So I haven't written this. So 2 and 1, so maybe I need a little bit more. So where? I have 8, I have and 13. So mod 3, it will be 2 and 1. And here it will be 1 and 3. No, 1 and 3 here. Yes. I cannot have two different solutions here. Sorry. So it's a 2 here. Okay. So I have this solution. So this will be 11. And 1 and 4, so it's 4. Okay? And in fact, so this is trivial root of unity. And the non-trivial root of unity is these two values. Okay, so you see that this solution is minus 1, 1, and that one is 1 minus 1. Okay? And if I use one of these two values, in fact, I will be able to factor. Okay? So basically, is the case. Okay, so by writing this, in fact, I will remove, in fact, this solution. Okay? I know that this solution is not possible, and with the second assumption, I will remove this solution. Okay, so this solution is a trivial root of unity, and it is not, in fact, important to factor. Okay? So in fact, to factor, we are interested in exactly finding this two solution, and you will see that if I have two different factors, I can have 4 different square roots, and 2 of them will be helpful for me to factor. And if I have more factors, so it will be in a much more, so the probability to find non-trivial root of unity will be higher. Okay, because here I have only 2 different factors. But if I have 3, for instance, I can have many, 1, 1, 1, it will be the trivial solution. Minus 1, minus 1, minus 1, it will be the minus 1 solution. But I can have many different solutions. I can have plus 1, minus 1, plus 1, or plus 1, minus 1, minus 1, and so on and so forth. And so with 3 factors, for instance, I have 6 possibilities to factor my number. Okay, so in total, I have 8 square roots of unity, but 2 of them is trivial, and 6 will be fine for me. Okay? And also, okay. So when I have one of these 2 square root, so it's very easy to factor. I just have to compute a GCD here. Okay, because I know that n divides this product, and n does not divide this term nor this term. And so n has to be split, in fact, into the 2 different terms here. Okay? So this is exactly the idea of the algorithm. But you can see that at some point it can fail with some probability, but it's not a big deal to fail. We can reduce the algorithm 2, 4 times if we want. Okay? So here I just show you exactly what happened. So I can use 2 because the order of 2 is 4. I have, in fact, 2 to the power 4 is 16, and it will be 1 mod 15. And the other, I don't remember. So I can have 11 also because the order is 2. Okay? The other solution will not be interested for me because the order will not be 2. Okay? Okay, so now I am just looking at the oracles that we will use. So we have to compute this function, but as usual, so this function is not, so the mapping, we have to make it inversible. So here the first element is the same, here, okay? And here I compute, in fact, a to the k mod n. It's okay?
Yeah, so we just say we'll have a small 2 minutes break so that if people want to shift, and just 1-2 minutes, or if you want to shift, and after we'll resume.
Okay, thank you, Ludovic. Ouais.
pour le bouquin.
Il faut que je le dise. OK. Can I continue? Yeah? Okay. So the mapping is very easy. So you see that I have only 4 different values here. And so this mapping, in fact, is not invertible. And so I have to remember, in fact, the input element. Okay? So that's why I put here all the elements here. And you see exactly that there is, so the period here is 4. That means that here you will always have all the elements. Okay? So how it works? So it works as we do this morning. So here we just remind, in fact, the register, with the first register, all the elements, so the bit decomposition of the element k, and this is the identity there. And for the second register, we begin with k 0 for each the different n line. And at some point, we will have, in fact, the bit decomposition of the output a to the k model. Okay? So here, I have not explained you how we compute this function here, because it's not an easy function, but I will explain you a little bit later. Okay? So the circuit is exactly as we do this morning for Simon's algorithm. So we begin with all k0 for the first n qubit. We apply Adama. At this point, we have a superposition of all qubits. Okay, so it's what is written there. And the second register contains only 0. I apply the function f, and so I get, after the oracle, in fact, this state. Okay, I have k here, and here a to the k mod n. Okay, so I remove the mod n here. At some point here, I will do a measure on the second register, and as we do this morning with Simon, so it will, in fact, fix some value, and we will get, in fact, here some partial measurement after some state after the partial measurement. Okay, so here I will assume a third assumption is that the order of A divide, in fact, 2 to the n. So it's the case here because here I took small n equal to 4. And so I have R which divide exactly 16. Okay? But in fact, I will explain you how we will able to remove this assumption a little bit later. Okay? So here, the state after the oracle is in fact this one. And now, in fact, I will compute the Euclidean division between K and R. Okay? And so I have, so the remainder will be beta, and the quotient will be alpha. Okay, so I know that the remainder is between 0 and R, and the quotient is in this set. And now here, in fact, I can write a to the k. I can replace this by this expression. And you say that since R is in fact the order of a to the R is equal to 1. And if I multiply this to the power alpha, it will remain the same. And so at this point, is exactly the same as a to the beta model. Okay? So this is, in fact, is the easy part. And here, for each beta, in fact, here, I will have, in fact, a lot of elements that map exactly to a to the beta. Okay? As this morning, in fact, you remember that we have 2 different terms on the output that map to the same output function. Here is exactly the same, except that we have a lot of different values and not 2 as this morning. Okay, so remember this morning we have a 2 to 1 function, and here the function is 2n divided by R to 1 function. Okay, so we have more input that map to the same output, and it is exactly what is written there. Okay, here you can see that for the output 1, here I will have in fact 4 different input. Okay, for the output 2 here, I have in fact 4 different input. Okay? So if I measure the second register here, in fact, it will collapse to some value, and the sum here, in fact, will disappear because I will select one of the R different beta, and at some point here, I have a sum of elements as we do this morning. Okay? And now, let me explain why we cannot just observe, in fact, the output. If we observe the output of the first register, we will get, in fact, here all the output will have exactly the same probability. And so we will have the same probability to observe one of all these states. Okay, so we know, so the second register, we know this value. Okay, so maybe beta 0 is not entirely known because beta 0, so you know that here we don't have beta 0, we have 8 to the beta 0 model. Okay, and if n is large, it could be very large. Okay, so we don't really know beta 0, but it's fixed. And here, for the first register, we will know, for instance, one of all these alpha. Okay, so in this set, all of these value, and we don't know exactly which one. Okay, but if I measure this, I will get one of the value. Okay, so for instance, if I observe, for instance, if the second register is a 2, okay, if I observe the first register, it could be 1, 5, 9, or 13. Okay, and if it is only 9, so I have alpha 0 and beta 0, but I have no information about the period. In order to have information about the period, I will need, in fact, to have two different values in this coset. Okay, and having two different values, that means that I will be able, in fact, to do the computation twice and observe twice the same second register. If I do the computation 2 times and twice the second register is beta 0, so this will be fine for me. Okay, but the probability to have twice the same output, it's extremely low. Okay, so we cannot just observe the first register, it's not sufficient to recover exactly the value. Okay, so but we will exactly as we do this morning for Simon's algorithm, so we apply the Hadamard. Here we will apply something that is a little bit more elaborate, it's the Fourier transform. Okay, so here, just remind you for this small example. So here, for instance, I observe, so before the observation, I can write the state like this. And once I observe the second register, maybe it will be 4. And if it's 4, that means that the first register will contain this superposition. Okay? So I will have, in fact, this superposition. And now, I need to do something, in fact, to recover the period. So you know that here, all elements are separated by the period, which is 4. Okay, and I need to recover 4. Okay? So for instance, here you see that R, in some sense, is an integer. And in fact, when we will apply, in fact, the Fourier transform, or the inverse Fourier transform, we'll be, in fact, able to transfer the period not in the numerator, but in the denominator, okay? Because, in fact, you are, in fact, trying to find some frequency, and the frequency will be 1 over the period, okay? So the idea is the following. So we will use, in fact, just the Fourier transform. So it's just an easy example. So here, you see that if z is equal to 1, so I have n term, and so this sum is equal to n. And if z is not equal to 1, so you see that this is a geometric sequences, and you know that the formula is like this. Okay, so it's a ghost trick, for instance. And in fact, if I divide this sum by n, in fact, I will get, in fact, 1 here. And if z is a nth root of unity, the denominator here will be 0. And so I will get 0. Okay, so this is, in fact, a useful thing to remark. So this sum, in fact, is equal either to 0 if in fact the value j here, g over n is not an integer, and if j divided by n is an integer, in fact, this sum here will be equal to 1. So it's something that will be helpful later. So this is just the Fourier transform and the inverse Fourier transform. So you just, in fact, put a -1 here according to this formula. So it's just the adjoint operator. And if you want to apply the FFT for for this state, in fact, this is a linear operator, and you just have to apply it on each separate term here. Okay? So now I will apply here, in fact, the inverse Fourier transform on the n first qubit here. And at some point, the register will be this one. Okay? So when I observe the value here, I will get this value. And in fact, if I got this value, the period r is in fact on the denominator of the fraction, and then I will be able to recover r. Okay, remind you that before applying the inverse Fourier transform, the r in fact is in the numerator of the function, and I have not been able to recover it. Okay? So here, so after the partial measurement, so the state is this one, and then I will apply in fact the inverse Fourier transform. So I can apply it for each term of the sum because of the linearity, and for each term, so this term will be in fact in the phases here. Okay, so it's what Thomas explained you in the beginning of this week. And so now I will swap in fact the two different sums here. So I will sum for j here. So it's not, so I am able to do this because this is in fact finite sum, so I can switch the two different signs. And here in fact, if you look at carefully, I can apply my lemma, and this sum will be equal to 0 if this term in fact is not an integer. And if it is an integer, the sum will be equal to 1. Okay, so here I can replace the big sum here just over the element g so that this value is an integer, and I can replace all of these parentheses with a 1, and it will transform in fact this according to this value. So here I just in fact write, so the integer here, I call it L, and so I will get in fact this, and j will be just replaced by 2 to the n times L divided by r. Okay, so here you can see that r is on the denominator of the fraction. Okay? And now, so now I can observe if I observe the first register, so I will get in fact one of all of this term and one of all of this integer, and from one of all of this integer, I will explain to you that how we can in fact recover the period r. Okay? So we measure the first register, so we will get in fact an integer here, and once we get an integer, so for instance it's called m, and in fact, so it will be one of all of this value, and now I will explain you how we can finish, so it's not too complicated. So this is in fact an integer, so this is something that is very useful to remember in this case. And this is an integer because r divides in fact 2n. So in fact here you see that 2n divided by r is an integer, and since L is also an integer, so it's the product of two integers, and m is an integer. Okay, so if I have this, I can divide m, so my integer, by 2 to the n, and in fact I will recover this fraction. Okay, and from this fraction, either in fact L and R have coprime, so the GCD between these two values is 1. So in this case, in fact, R is the denominator of the fraction, so I recover R exactly. And in the second case, in fact, so the two elements are not coprime, but in fact, I can recover this fraction, and from this fraction, in fact, I will recover R prime, which is a factor of R. Okay, and once I have a factor of R, in fact, I can reduce the algorithm with just this element to recover the remainder of the period. Okay? So you understand how it works? Okay, so now I explain you how we can implement the oracle. So the oracle, I just recall you that we have in fact to compute a to the x mod n. Okay, so this is a very special trick in cryptography, so, but I think a lot of you know. So in fact to compute a to the x, so the idea is to compute the binary decomposition of x. Okay, and here I have a to some sum of value. So remind that xi here is just 0 or 1. Okay, and this is a to the x. And so a to some sum here, I can replace it by the product over I of all of these terms. Okay, so in fact, and here I just call a to the 2a mod n. In fact, I call this value ai. So assume that we pre-compute, in fact, all of these values. There is not a lot of them. For instance, if we have here n, which is a 128-bit value, so we only have 128 different terms here. And so here, we do what is called, in fact, a multi-product. Okay, so it's not an exponentiation, it's a control multi-product that we are computing. Okay, so according to the bit xi, if it is 0 or 1, we multiply by the value. Okay, so here you can see that it's very easy. Oh, sorry, here, I think we don't begin with a 0, if in fact we begin with a 1, but you just apply a knot on the first, for instance, qubit. And here, if x0 is 1, in fact, we will apply this a0. If it is a 0, we don't do anything. And here, if x1 is a 1, we apply this function. Otherwise, we don't multiply by x1. And here also is the same. At the end, we have computed this function. Okay? So here, in fact, you can see that we can, in fact, compute this control multiproduct just by using so this different gate, and it's just controlled by the bit of the exponent x. Okay? Do you have any question? No? And in fact, there will be a lot of progress in the factorization algorithm, and in fact, a lot different by the implementation of the oracle. Okay? So now, I explain you that we are able to compute, in fact, the order when the order divides 2 to the n. Okay, but it's a very unlikely event, and so I have to explain you how we can do this in general. Okay, so for instance, if r divides 2n, it's what I called you. So in fact, this value is an integer because r divides 2n, okay, and L is an integer there. And so I can, in fact, compute x, which is this fraction. And when I have this fraction, I can represent it into a much smaller element, and the denominator will be r or a factor of r. Okay? So now, and in fact, you can see that the value x that I got here is in fact a multiple of 1 over r. Okay, so I am in a good situation. Now, if r is not divisible by 2 to the n, I cannot say that the integer that I got, I remind you that after my second observation, so I have n different qubits, and it defines me some integer. Okay? But this integer, it's not exactly this integer. It's close, in fact, to this value because this is, in fact, not an integer, but a rational value. Okay, so I have an integer that is close to this rational. Okay, and in fact, so this is not anymore an integer. Okay, so when I divide the integer here by 2 to the n, in fact, I have not an exact multiple of 1 over r. I have only a close to a multiple of 1 over r. Okay, so this is not an exact multiple of 1 over r, and our goal, in fact, is to find, given this rational, in fact, what can be, in fact, the best, it is close to some fraction, but what is the closest fraction that is close to this rational value? Okay, and for this, we need, in fact, to know a little bit more math. So it's what is called a continued fraction. So it's a very useful tool that allows you to find, in some sense, the best rational approximation of some rational or real value. Okay, so this is a very useful tool. And for instance, you can use it to compute what is the best rational approximation of pi if you want. Okay, or exponential, and so on and so forth. So the idea of continued fraction is you can always, so here all the AI are integer, and so you have a whole sequence here of integer that represents this fraction. Okay, so here you have the constant, so this is the integral part of the fraction, and here it will be the remainder of the fraction, and it can be decomposed into this part. So you can take any fraction and represent it like this. Okay. Another thing that is useful is that I can, so for instance, this sequence can represent this fraction, and you can see that this is a very, very long fraction here. And at some point, so maybe it's not repeated again. And what is also useful is to look at, in fact, so this is a whole sequence, but I can, in fact, just take some part of this sequence. For instance, if I take only the first part, so you see here that I select only the integral part of the fraction. Okay, if I take the two different values, I have this approximation, and now, so this is not exactly the correct term here, but I have an approximation of this fraction. If I took the first integer of this value, I have something that is going closer and closer to the fraction. Okay, so this, the beginning of the term is what is called the convergent of the fraction. Okay, so they are getting closer and closer to the fraction. Okay, so if you want to have a good approximation of pi, for instance, so one idea is to write this as follows. So if you want to have the first two digits, you can write it as 314 divided by 100. Okay, but here, in fact, you see that the denominator is very large, is of order 100. Okay, but this is a fraction, and you can try to decompose it into this continued fraction, and you will see that, in fact, you will get this set of these sequences. And if I take only the two first terms, so you have 3, because pi, so integral part of pi is 3, and this I have 1 over 7. And so maybe a lot of you know that 22 divided by 7 is a good approximation of pi. But if you want to have a better approximation of pi, you can see that you can take also the 4 first term of this fraction. So and if, in fact, here, you can see that I have, in fact, 6 digits that are correct. Okay? And you see that I have 6 correct digits, and the size of the denominator is about the same as the size of the denominator from this fraction. Okay? But you see that with this fraction, I only have 2 digits after the commas that are correct, while here I have about, with a denominator of about the same size, now I have 6 digits after the commas that are correct. Okay, so you see that continued fraction allows you, in fact, to have a better approximation of fraction or any other real value. Okay, so in fact we are exactly using this tool because we are in fact trying to find some fraction that is close to another fraction. Okay, and we are in fact trying to find one of these fractions with a denominator that is the smaller one. Okay, so for instance, if you want to try to factor 21, now n is much larger, and the order of 2, in fact, is much larger, and the order of 2 does not divide this value. Okay, so we are not in the same situation as for when I try to factor 15. Okay, so, but the output of the first register assumes that it will be this value. So I will get, in fact, m, the value m, so the value of the register. So it's an integer. It's close to some rational value, but it's not exactly the value. Okay? So for instance, if I divide just as before this value by 2 to the n, I will get this value. One thing that you can do is that it's about 4 divided by 5. Okay? But if you do this, it will not give you exactly the order, the right order, because 5 is not the correct value. Okay, so in this situation, in fact, the order is 6, because 2 to the 6 is 64, and 64 is in fact 1 plus 3 times 21. Okay? So in fact, the order that we are looking for is 6 and not 5. Okay? So in fact, one thing that we can do is we take this fraction and we compute its continued fraction that correspond to this fraction here. So here you can see that the integral part of the fraction is 0. So the first digit will be 0. After we will have 1, and so on and so forth. And this is the first, in fact, convergent of the fraction. And in fact, since we know that the order that we are looking for is smaller than n, and n is 21, we know that here we are looking for a value that is smaller than 21. And here you see that the value that we have on the denominator is larger than 21. Okay, so if we go up to this value, so we are above 21, and so we have to stop before, and here 6 in fact give you the correct value for the order R. Okay, so I explain you that the order of A is equal to 6, and it is exactly the value that I'm looking for. Okay? So I do exactly the same kind of algorithm, but the only things that change is at the end, I have to do something a little bit more clever. Okay, and what changed, in fact, is that, as I apply the algorithm, Shor algorithm, here you can see that all the different lines here will not have the same number of terms. For instance, the two first lines have 86 terms, while all the line, the row here, have only 85 different terms. And it will make the situation a little bit different. Okay, so after the FFT, I will get this value. And nowadays, it's no more the case that the lemma that I apply, that this sum will be equal to 0 or 1. Okay, this sum, in fact, will be something that is not exactly 0 or 1. Okay, so for instance, if I plot all the value here, so you can see that the value here are not 0 or 1. So you see that it seems to be 0, but it's not exactly 0. You see that I plot all the probability around this peak here, and you see that around this peak, so I have here the peak will be at 427, and I have the highest probability, but this probability also is quite high, while all the other value after is low, but not exactly 0. Okay? And that means that if I am observing now the first register, so this is in fact the phase, and according to the phase, or the eye of the peak here, maybe I will get in fact the value here. Okay, so the value here, so the value m, the integers that I will recover, maybe will be that one. So it will be 427. Okay, and I showed you that I am able to do this. Okay, so here is some theorems, which is a well-known theorem, and also it's helpful in cryptography to apply it and to remember it. If you have some x is some rational, but if it is some rational, it also works. So if you have some fraction, and if you are looking for some value and some fraction, and the fraction in fact satisfy this equality, so you know that the denominator here, q, in fact, the distance between the two is below 1/2 divided by q squared. In fact, if you are trying to compute the continued fraction of the value x, in fact, one of the convergent of this fraction will be exactly the good fractions that you are looking at. Okay? So in fact, that means that, in fact, in order to apply this theorem, in fact, what changed is that we need to have this situation. In order to apply here, in fact, you need to be in this situation. So in this situation, you know that you need to have that, in fact, the number of bits that you begin with, in fact, is larger than the square of n. And if you are, this equation is satisfied, so you are in the business, and you can, in fact, recover the order of the element are in this situation. Okay, but it can fail. Okay, if the order here that you recover is not even, so you have to reduce the whole algorithm one again with another integer a. Okay? It is okay for you? Okay, so this is exactly a Shor algorithm and how it works. So this is, in fact, so you see that Shor or Simons can always be described by what is called the hidden subgroup problem. So you have a group and you have a subgroup H of this group, and you have some functions that is constant of each coset of H. So so the coset is just the set of all elements that we have for the first register. Okay, for Simon's algorithm, we have coset with two elements, x and x XOR c. For Shor algorithm, you see that the coset can be as large as the period R. Okay, so it's another kind. And this is a special case of this algorithm, which is a hidden subgroup problem. So it just, so the HSP algorithm is just, in fact, Shor in a more abstract way, but you can, in fact, embed a lot of algorithm in this setting. Okay, and Kita F also explain you that if you have G is, in fact, an abelian group, you can always apply such an algorithm, in fact. Okay, but what happened for a non-abelian group? And it is something that is very helpful, in fact, and something that is helpful, one of the most interesting maybe non-abelian group is, in fact, the dihedral group, and we have what is called the dihedral HSP problem. And for this non-abelian group, in fact, there is an algorithm that is not polynomial nor exponential. It's sub-exponential, so in between, exactly like the factorization. And so it requires some step, but it's not as the exponential value. And it allows you, in fact, to solve the problem. Okay? And it's something that is very helpful because, in fact, I speak about the LW, so the lattice problem this morning, and I show you that lattice problem, in fact, we hope that the problems are hard to solve. And one of the lattice problems that is used in cryptography is the LWE scheme. And the LWE scheme, in fact, is an average problem that is as hard as some lattice problems, that is very hard. And in fact, it is possible to reduce the resolution of this problem into not exactly the dihedral HSP problem, because if it will be the case, in fact, you will have, in fact, a sub-exponential algorithm to solve LWE. But in fact, it is a stronger version of the dihedral problem because for the dihedral problem, you don't have too many errors. And in fact, if we can reduce this to this problem, but in fact, for this stronger version, we don't know noiseless version of Kuperberg algorithm to solve it. Okay, so this is very interesting to see that, in fact, the link between the Kuperberg algorithm and the LWE problem, and it is something that is very helpful. I don't know if it's possible to improve Kuperberg algorithm in this situation. Okay, and so a lot of people try to improve, in fact, the implementation of Shor algorithm up to 2020. And in fact, in 2020, so the best paper and best evaluation have been given by Craig Gidney and Martin Ekera, and they show that, in fact, you need 20 million noisy qubit and with 8 hours, in fact, to factor a 2048-bit RSA modulus. Okay, so we think that we are safe up to some point, but maybe it will not be the case. Okay, so this is in the best result in 2020. So, however, there are more interesting results. And so the best approximation of Shor algorithm requires, in fact, 2 n qubits. So n, in fact, is the size of the modulus. So you need, in fact, more than 6,000 logical qubits here to apply Shor algorithm. So these 6,000 qubits, in fact, represent 20 million qubits. And in fact, here is the cost of the algorithm. In fact, so this is maybe a cheating part because the best implementation, in fact, don't use fast multiplication implementation. They use, in fact, school book algorithm, and so the complexity is more about n to the cube. Okay, so it's a little bit cheating, but it's a complexity just to compare with the other algorithm. Okay, so there is in 2023, in fact, Oded Regev, so 3 years after the evaluation by Ekera and Gidney, shows that a new algorithm where the complexity, the number of qubits is larger than for Shor algorithm. So you lose, in fact, square root of n qubit. So here it's much, much larger. But in fact, you see that the circuit can be reduced by a square root of n. And in fact, the number of, you have to run the algorithm much more time, square root of n also. Okay, so in fact, since the circuit is smaller, you think that it's maybe easier to run the algorithm because even if you have some error sometime, in fact, the error will not impact so the output if the circuit is smaller. Okay, so this is what he is hoping. And so he needs to run the algorithm so many times. And at first, in fact, you need for each different of these square root of n run, no error. Okay, so this is a very strong assumption, but this assumption, in fact, can be removed. Okay, so and 1 year later, in 2024, in fact, Raghavan and Vaikuthanathan shows that, in fact, you can improve the number of qubits here, not exactly as short as for Shor algorithm, but 3 times, more than 3 times larger. So the number of gates is about the same. In fact, the constant here is a little bit larger, but not too much. Here the constant, in fact, is 3, I think, while here it's 50. But here, in fact, the number of runs is exactly the same, but in fact here, there is a new procedure that allows you to detect when there is some error. Okay? So in fact, here, Regev algorithm cannot afford to have some error for each of the runs here. Here, the run you can have some error sometime, and you can correct them. Okay, so this is so there is a filtering procedure there. And lastly, last year and this year it will be published. We have a new algorithm where, in fact, the number of qubits is reduced. So we go from 3n qubits to n/2 plus a little bit. So maybe I will explain you. So the number of gates is exactly the same, but in fact, you can see that is n cubed. And in fact, so the number of runs for our algorithm is constant. Okay, so it's 40 or 50. Okay, so maybe now I have maybe I can try to explain you how Regev algorithm is working. So Shor algorithm remind you that I begin with some value and I compute the order of 4. Okay, I begin with 4 because I know that 4 is 2 to the 2, so I know that I ensure that I will be able, in fact, to compute the square root at some point. Okay? So now, if I compute it, so I did it with my computer, and so the order is close to 1,000. Okay? So the order, so I did it for this module. Okay? And so it's not exactly n, but it's very large. Okay? And if I got this value, so you can see that I can always factor, because now I can easily compute a square root of this value. It will be 2 to the order. And if this is a non-trivial square root of 1, I will be able to factor. And exactly it's what will happen. Okay? So this is good. It works perfectly. So now Regev algorithm is in fact a generalization of Shor algorithm. So it's a little bit different. And then instead of just computing 4 to the z1, it computed 4 to the z1 times 9 to the z2. Okay, so here I have 2 squares, so it's easy to compute a square root, one again. And for instance, here I just show you some of the values that I computed. And if you look at carefully, here I have 1, 9, 81, 7, 29. And here you can see that you have exactly the same period here. Okay, and for the second line, you have 4, 36, etc. And I have 4, 36, etc., etc. Okay, so I computed all this row, and now I have a 2-dimensional period, but it's not a big deal. I can always apply Shor algorithm for 2-dimensional period. And now I can find that this order on this instance, in fact, is 2715. So what you can effectively look at is that the period is much, much shorter than what the period you have here. Okay, and this is very helpful because you know that for Shor algorithm, you have to raise the value up to some point, which is close to n. Here, we will be able, in fact, to compute the to raise the value, but the value where we are raising the value will be much shorter. What does it mean? Is that when you have to implement your oracle, you don't have to have too many multiplication, multi-product, control multi-product. So the number of control multi-product will be much, much shorter. Okay? And this is a very helpful thing. Okay, but in my case, so you can see that sometimes it does not work. And exactly it's the case here. I obtain -1. And -1 is a root of unity, square root of unity, but it's not a non-trivial square root of unity. However, it's not a big deal. I can try to find another period, and I can find that one. So it's not as short as this one, but it's also short. And in fact, here, I recover some things that allows me to factor. Okay? So this is, in fact, a 2-dimensional period. So I rose 2 to the power 19 and 3, which is a square root of 9 to the power 47. I compute this value modulo this RSA modulus, and it will give me this value, which is a non-trivial square root of this value. Okay, so the end of the algorithm is very similar of what we expect, except that now we are running, we are looking for period in higher dimensional. Okay? So as before, so the first step is the Hadamard. The FFT, the inverse FFT at the end, you have to observe exactly as before. And so the most expensive step that I have to implement is in fact this multi-evaluation. Okay? So here, but I recall you that I only have to raise here to some power Z1 and ZD, and the size of ZI are much, much shorter than the size of Z for Shor algorithm. Okay? So here we are in dimension D, and we only have to raise the power up to 2 to the n over D, okay, to look at the period. So it's a basic theorem, so it's just a pinch-in all value, because if I have D value, and if I have a 2 to the n over 2 D to the power D, so I will give me, in fact, 2 to the n different value, and from this 2 to the n different value, I am sure that the period will appear somewhere. Okay? But in fact, we have to do this D time. Okay? Because I have to compute this value up to the I of size 2 to the n over D, but I have also to compute this product, and so I have to do this computation D time. Okay? So I'm not sure that it will be helpful for me. Okay? So the idea is, it's well known in cryptography, is that when you have to do this computation, in fact, you can do this much more efficiently. Okay, so the first thing that you have to do is that you begin with the first square of the first prime. So you have 4, 9, 25, 49, etc. So this is all the value that you have. And now, so the first thing that you do is that you compute all the subset, the possible subset here, okay, of this 8 value. Okay, so you have A1, A2, A3, but you have also to compute A1, A2, A3, A4, and so on for all of these values. So it's not a big number of value, and there is a very clever way to do this efficiently here using some product tree. It's very efficient. And now I will explain you how you can compute this value. So to compute this value is not too complicated. So you start from this value, and I will just explain you how you compute this. Okay, and now you look at, in fact, the most significant bit of all of the exponent. The most significant bit of all this exponent, so this is a 4-bit, in fact, exponent. So this is a 1 here and a 1 here. So I multiply by A1, A2 here, and I will get this value. Now I compute a square from this value. So I have 2 here, 0, 0. And now I will look at the third bit on the binary exponentiation of this one. Okay, so I will have a 1 here for the second bit. I will have 0, 0, and a 1 here. So I will raise to the power, I will multiply by A1, A4, so I will get this value. So you see that I have 1 here, and I have 3 here. Now I compute the square, and I have this value here. I just multiply by 2 all exponent. I look at the third bit, and the third bit will be, in fact, 0, 1, 1, 0 for this exponent. So I multiply by this value. So I have 1 here and 3 here. I compute a square 1 again. And now I just multiply by this value for the last bit of all these values. Okay? So this is, so you see that I can, in fact, if the exponent here is as large as 2 to the n divided by d, in fact, here I just have n divided by d multiplication and squaring. Okay? So it's basically 2n divided by t. Okay. And the final step, in fact, so you see that I am in a much larger dimension, and so it's not exactly the continued fraction. So continued fraction in a mathematical way. So if some of you are doing lattices, so it is exactly a very easy version of lattice reduction in dimension 2, and in a more general dimension is what is called LLL that is used. Okay? So, but LLL, you can think that it exactly as the post-processing of Simon's algorithm. You need, in fact, in Simon to have n minus 1 different value to recover S. Here, in fact, I need as many vectors as the size of the dimension that I am looking at. Okay, so I need, in fact, d vector, correct? So d, in fact, here will be, in fact, the number of runs that I have to apply my algorithm. Okay? So I apply, however, LLL is not as efficient as lattice dimension in dimension 2. So in dimension 2, lattice problems are very easy, but in higher dimension, so LLL is not as good as continued fraction, and so we lose some approximation here. So, and it's something that is very special on lattices. In fact, the hard problem is not only hard problem, as for instance for the traveling salesman problem, but they are also hard to approximate. Okay, for the TSP problem, you know that there is a well-known 3/2 approximation in polynomial time. Here for lattices is much, much more difficult. You don't have a polynomial approximation factor, and the only in polynomial time, the best approximation factor that you have is exponential in the dimension. Okay, so that means that I have to take, in fact, the exponent a little bit more larger. I have to multiply the size of the exponent by a factor 2 to the d. Okay? And now, what is the best? So I remind you that this is the more larger that is this exponent, the more number of control multi-product I have to do. So I have to make this value the smallest as possible. And so to make it the smallest as possible, so you have two different terms, and the optimal is when the two terms are equal. And so in this case, you can see that d will be a square root of n. And so if d is square root of n, I will explain you why, in fact, I need n to the 3/2 qubit. But in fact, you need to run the algorithm square root of n, because in fact, as for Simon's algorithm, you need to recover as many vectors as possible. Okay? So now the algorithm is exactly the same. I begin with the first square of the first prime here. So I go up to this value. So for n equal 248 is not too much. So I run, so the oracle, so I compute my Adama, I compute my oracle, so I compute this value in superposition to all of the different qubit, and I have to go up to this dimension. I measure the second register, I apply the inverse QFT, and I got something vectors that are in the dual of the lattice, and in fact I can apply LLL at the end to recover the period. Once I have the period, I just raise some value to the value of the period, and then I compute some GCD. Okay, so the end is exactly the same. Okay, but I will explain you why now the number of qubits is so large. Okay, so why the number of qubits is so large is because of this implementation here. So from this implementation, you have multiplication, square multiplication, square multiplication. You have seen that for Shor algorithm, in fact, we pre-compute all of the A2 something. In fact, here for this algorithm, all of this value can be pre-computed once. Okay? But the main complicated part is this squaring phase. In fact, squaring is not a permutation. Okay, you have two different values that are mapped to the same output, and in fact, it's not easy. Okay, so if this squaring is not possible, in fact, each time you square, you have to remember the value and the square of the value. Okay, so for instance, you begin with A in some register, and after the first squaring, you have to remember A and A square mod n. And after the second squaring, you have to remember A square, and A4, and so on and so forth. And since I told you that you have to do this n over d time, so square root of n time, so the number of the bits that you need, the qubits that you need to register, in fact, is as large. Here you need n qubit, and you need n times d, or n times square root of n qubit. And so the number of qubits that you need at the end is n to the power 3 over 2. Okay? Is n times square root of n. Okay? Because of the squaring, you have to, and it's not a reversible operation, and you need to register all the squares that you compute. Okay? So this is Regev algorithm, and it's why the number of qubits is large. Okay? But in fact, Raghavan and Vaikuthanathan, in fact, describe, in fact, a very smart way, in fact, to do the computation. Okay, so they observe that the squaring is not reversible, and it's the main drawback for a Regev algorithm, because you need so many qubits. And so they develop a smart way to do the exponentiation without having to square the value. Okay? And the idea comes from what has been described in 2017 by Kaczynski. In fact, he used, in fact, some Fibonacci number. Okay, so I think that all of you know a Fibonacci number. So you begin with 1, 1. So you have 1, 1, and you have here the sum of the two previous value. So the sum of the two previous value, you will get all these value, etc., etc. And this is a very good set of integer, and you can, for each different integer here, you can always represent it as a sum of Fibonacci number. Okay, so it's not too difficult. For instance, if you have to represent 25 using just Fibonacci number, you took the first Fibonacci number just below it. Okay, so it will be 21. And so here, what is the remainder? It will be 4. And 4, in fact, what is the Fibonacci number less than 4? It will be 3. And after, it will be 1. Okay? So you can take any number like this. So it's just a greedy algorithm. It's not too difficult to write it. And now we just want to do multiplication. Okay? And so now the idea is that we are able, in fact, to compute all of this operation, in fact, quite easily. And so using just a 2 register accumulator. And so, for instance, if you have these two values, you can, in fact, compute A to the power. So this is k plus 2 Fibonacci number. And from this value, I can also compute here in this register, in fact, f k plus 3, because you just have to multiply. And multiplication is okay. You modular multiplication. You can do modular multiplication, so they are reversible operation. Okay. So the only thing that you have to deal with is that at some point, maybe you will find some values that are not invertible. Okay, because you are multiplicating a lot of things, and at some point, maybe it will not be the case. And so this is something that I've been explained by Shaw. You can, in fact, do the whole computation. In fact, you have to certify that the value A and B here are invertible value in order so that the multiplication here is invertible. And to do this, you also have to remainder the inverse of all of these values. Okay, so this will cost you a little, but not too much compared to Regev algorithm, where at each squaring, it has to remainder n qubit each time. Okay? And here, in fact, so you see that you have to do a little bit more multiplication using Fibonacci number. And so the number of multiplication is larger for Ragavan and Vaikuthanathan algorithm than the one for Regev. Okay, so it's normal. The number of multiplication increase, but you have no squaring here. Okay? And also, they have been able to improve the last step using a very trivial filtering operation where they can, in fact, remove some error at some point. Okay? So in Regev algorithm, all run has to be without any too much error. So the error has to be located around the right value. Here, if there is some error sometime, so there is a procedure to remove all the wrong error. Okay, so this is a very helpful solution. Okay, so let me introduce what we did, in fact, with my co-author. So, and it will be published next month. So, in fact, we are not interested in reducing the size of the circuit, but we are interested in reducing the number of qubits. And so we will show that it's possible to factorize using only n over 2 qubit plus something, okay? And the number of gates will be that one, okay? But it's like Shor algorithm if you use a schoolbook algorithm. Okay, so in our case, we'll show that we are able to use such many. So the little o here is a little o, but it's not as little as we hope. And so what is also costly when you implement is a Toffoli gate that is much more costly than just a NOT or an Hadamard gate. Or it will depend on the architecture, so I'm not an expert here, but usually Toffoli gates are very costly, and so that's why it's important to compute exactly the number of Toffoli gates. Okay? And what we show that, in fact, the oracle is just completely classical, okay? There is no fancy stuff, okay? And quite recently, 1 month ago, Craig Gilney, in fact, here again, in fact, improved our result. So he shows that, in fact, he can reduce the number of logical qubits up to this point. So he saved 300 qubits, in fact, logical qubits. And in our work, in fact, we compute the LSB of some value. And here, so the LSB is the least significant bit. And he shows that it's better to compute, in fact, the most significant bit of the value. And he also reduced the number of Toffoli gates and also the number of runs. Okay, so it's something that is much more practical. And so now he shows that he can improve, in fact, the number of noisy qubits from 20 million noisy qubits up to less 1 million qubits. Okay, so we gain a factor 20 at some point. Okay, so this is a very impressive result. And so how algorithms work so it's, in fact, we are not interested in our case to compute the period of one element. We are, in fact, interested in solving the discrete log problem. So maybe it's a good opportunity to show you how it works with Shor algorithm. So assume that you want to find D such that A is equal to G to the D modulo some integer. Okay? So the idea here is to come up with this periodic function. Okay, so we have a two-dimensional function, and the value that we compute is G to the X times A to the minus Y. Okay, so here it's just the inverse of A to the power Y. Okay, so X and Y here are two integers, and then if I replace A by this value, so here, so you can always write this value in order of in base G. And you can see that if I add D on the first component and 1 on the second, you can see that I compute exactly the same value here. Okay, so here I will have x plus d, and here I will have minus d times y plus 1. Okay, so the d and minus d will cancel out, and at the end I will have exactly the same value. Okay, so this is the main idea to compute the discrete log. And so the idea is the same. We have to compute this function. And to evaluate this function is one again a control multi-product. Okay, so this is the way we have to implement it. Okay, and Ekera and Ashtat have shown how to solve this. So this is not so it's something that was in fact well known in the literature, but they did it in fact in 2017. So in fact we will embed in fact so the value of the discrete logs that we are looking for is in fact p plus q. And if I give you p plus q, in fact, it will be easy to factor n. So I will explain you a little bit later. And in fact, what they show is that we can, in fact, compute discrete log. So this is, in fact, the classical Shor algorithm for discrete log. But more importantly, they show that here, in fact, you see that if d is small, so if the discrete log is small, here also you see that the period is very small. In fact, the number of registers can be as low as this value. So you need n over 2 here because this is the size of the discrete log here that you are looking for. But the second value here can be very small because it corresponds to the 1 here. Okay? And if you do this using s plus 1 time, so as Simon at the end, in fact, using a post-processing stage, you can in fact recover the discrete log. So the post-processing stage is something that is well known in cryptography, which is you have to solve in fact a hidden number problem, and it's something that we know how to solve it very efficiently using lattices. So why in fact, if I give you p plus q, it's easy to factor? I don't know if you know this, but it's a well-known fact in crypto. So I give you, yeah? Yeah, exactly, yeah. So I give you the sum of I give you the sum of two values here, and I give you the product of two values, so you just have a simple equation to solve. Okay? So this is very easy. And here it will be the case. Okay, so how can we put, in fact, in the exponent the discrete log? So now it's not too complicated. So we took at input some element, and we hope that the order is larger, in fact, than the discrete log that we are looking for. Okay, so here there is a half of the value, but it's not, basically you can think of it is p plus q. Okay, and if I raise, in fact, g to this exponent, in fact, you can see that in the exponent, I can remove some value phi of n because it will not change all value to the power phi of n, or maybe phi of n divisible by 2 because it's the exponent of the group, but trust me, it will be the case. So you can see that the output of the discrete log here will be this value. Okay, and if I recover this value, so once I have this value, so I can recover phi of n, or I have recovered easily p plus q. Okay, and once p plus q is known, so I can factor. Okay, so now I just have to compute this short discrete log. Okay, and at the end, I have a post-processing stage. So in fact, in our scheme, we will use also another tool that have been developed by May and Schlipper, and that, in fact, they show that if you compute if you have some periodic function, and you truncate the function maybe up to some bit at the output, it's still a periodic function. So it's a basic, maybe you will have false alarm, but it's still a periodic function, it will help you. Okay, and this is exactly what we will do. In fact, we will not compute a to the k mod n. We will compute, in fact, some exponentiation modulo. So we are computing, in fact, the least significant bit of this value. Okay, and it is exactly where Guinea, in fact, compute the most significant bit of this value, and he can do this using cheaper arithmetic. Okay, so this is why he can save something in order of value. And so our main result is that how we can do all of this value using only a small amount of space. Okay, so this is in fact what we show in our paper, and Guinea show another kind of result. Okay, but this is exactly our result. Okay, yeah. Yeah, exactly. So the f here is the periodic function that we are evaluating. Okay, so here the periodic function is this one. It's a little bit more complicated than this one because we have to compute this function. Okay, but it's the truncation version of this function. In fact, you need less qubit, in fact, in the circuit to evaluate it. Okay, so here, in fact, if you compute this mod n, so because I don't compute the value and then I truncate. I do the whole computation with very small memory. And so because I can show that I can compute not this value, but this value mod 2 to the r using small of n space. Okay? So yeah. So it's a good question. Yeah, maybe I was not clear. Okay. So this is exactly the goal. Okay. So I hope that I showed you that it's very interesting looking at the security of Shor algorithm because there is still a lot of improvements that we can do. And so Regev achieved one part, and we achieve another part, and maybe there is more clever improvement or speed up that we can gain, and maybe it will lower the number of qubits logical qubits that we need. Okay? So we are expecting that people will be able to construct a larger computer computing. I just showed this afternoon that now IBM expect to have, I don't remember, maybe 1,000 qubit, logical qubit for 2029. So maybe at some point it's not too far from what we need. Okay? So we will see in 4 years if I've been able to do this. Maybe not 4 years, but I think in less than 10 years, maybe it will be the case. Okay? Do you have any question? More question? No? So maybe I have just time to show you, speak about Grover algorithm. Yeah? Yeah. Yeah, so I think it's, what is a bit difference between, the number of, how many noisy qubit you need to implement correctly a logical qubit. Okay. Yeah. Normally it's 10,000. Yeah, okay, but I mean, when you said that we could compute so that way with 1 million noisy qubits, does it mean physical qubits? It means physical qubit, yeah, exactly. So it's, the numbers that Guinea evaluated, so Guinea shows that for his paper here, with less than 1 million noisy qubit, you need in fact 100 and 400 logical qubit. Okay, so it's, you see that it's more than 10,000. No, it's less. Okay, yes, maybe it's less than So for one logical qubit, you need less than 10,000 qubits, okay? But I think that you have to look carefully at the architecture and to know how he can do things. But he developed everything and he go on the physical level, and so it's a very interesting paper, I think. Okay, but you can see that it's a very circuit optimization sometimes. So it's people that are doing circuit optimization that can do this. Yeah?
You mentioned the Cooper paper on the diagonal group for the human subgroup problem. Is there interest to extend this kind of result to other non-human groups? Like a proof of concept.
To non-abelian group, there is a Kuperberg algorithm that I showed before. I don't know other kind of result, but I think it's maybe possible. There is some variant, I think, of this algorithm.
I think the question is whether it was interesting, and I...
Yeah. If it was just like a proof of concept that you can do some non-polynomial functional algorithms for non-abelian groups, or if there is a research that people do to expand this algorithm to...
Yeah, there is a research that people try to obtain. Okay? So now I will move to I don't know. Oops. Sorry. Yeah, thank you. So I hope it's working now for this slide. So we'll explain you how works a Grover algorithm, and if we have time, some application on cryptanalysis also. So Grover algorithm is used, in fact, to search in some list of items, and so most of you know that if you can sort the list, you can use binary search to find some element. If you can compare elements, so it's very easy. You can do this in log of the size of the list. If the list cannot be sorted, you have to look for some element, and it will take you order of n. And you can, in fact, Grover algorithm can do this, in fact, in square root of n. Okay? So the algorithm is probabilistic. So at some point, there is some probability, but the probability can be made very low. Okay? And so it's a very interesting algorithm, and it has nice application in symmetric crypto. So a lot of people have presented this kind of slide to illustrate how it works. So here you have 3 qubits. So you have 8 different elements, and you want, in fact, to look at for a specific value. Also, something that maybe it's worth to mention is that Grover algorithm can be used to recover one element in a list, but if you have looking for many different elements, so in fact the probability can be higher and it can be also adapted. Okay, so the probability, it's not too difficult to generalize this algorithm if you are looking for one among some elements. So the first idea is that, so this is in Grover paper, so it shows that the first operation, in fact, for each different qubit here, so state here, sorry, So this state, if it is the state that we are looking for, the first thing is that we compute some symmetry according to this axis. Okay, so this is an operation that we have to do globally on the whole state, and we will apply, in fact, the oracle on the whole state. Okay, but as before, we will begin with the sum of all different qubits, and so we will apply an Hadamard gate, okay, to have a superposition of all the different possible values. Okay, so at some point we will apply this symmetry, and now we are computing, in fact, in some way, the average of all of the different values. Okay, if you compute the average, so you see that the average will be, in fact, below all of these values because we have a negative value here, but the mean will be about the same here. Okay, so this is maybe a cheating drawing. And now we are doing some symmetry according to the axis here, according to the mean. Okay, what does it mean is that all of these values will be below the mean, okay, with some value, but this value that is much smaller than this, it will be higher, okay? So this is the goal of one step of Grover algorithm, okay? And at some point, you will be in this situation after one step, okay? But if you go with a lot of different value, here maybe the probability to have this state is still very low, and so it maybe is noisy in all of this noise, and so you will need, in fact, to apply the algorithm one more time, 2 times, etc., so that at the end the probability to have this specific qubit will be high enough. Okay, so this is the basic idea of the algorithm. Okay? It is okay? Okay, so I have now to explain you how it works. So basically, the idea is the following. You start here with the superposition of all the different values, and here you have n qubit, and at the end, here, on the n qubit, you will observe the index of the values that you are looking for. Okay, so on this n qubit, you will have n bit, and this n bit corresponds to the right value. Okay, for instance, with the example before, I have 3 qubits, so I have 8 different values, and at the end of the algorithm, I need to have, in fact, the index that can be describing using only 3 bits. Okay? So at the end, I will observe here the bit decomposition of the index. So I begin with the superposition of all different values. So here I will have 2 to the n value. Okay? The slide before, I have only 8 values. And here I have another qubit, in fact, that is initialized with 1. And here I apply also a Hadamard state. Okay? And after, I will have a lot of Grover steps in order to make the amplitude of the correct value high enough. Okay? And what is exactly the value here? So the value here is n qubit here and 1 qubit here. And here I have n qubit and 1 qubit. And in fact, this is this step. Okay, so this step is, here is the oracle, Grover oracle function, so it's very easy. And here is some symmetry that we apply. Okay, so the Grover oracle function is, the idea is to put, in fact, the value, a symmetry according to the x-axis, and the symmetry here will be, in fact, the symmetry according to the mean. Okay, so it's the second step that we use. And in fact, we need, in fact, to apply it a square root of time, of capital N time. So here, capital N, in fact, is 2 to the small n. Okay, and with this probability, we are able to recover the index. So this, as we will apply it with n very, very large, so this probability is very close to 1, okay? So if you want to stop before, you can do, but the probability will be less. Okay, so how it works? So the first thing that you do is that after the Hadamard state, so the first n qubit will represent all of the value, and then, in fact, we will split this whole sum into two different values. So here we'll have the correct index that we are looking at, and here we'll have the sum of all of the different values. Okay? So here, so the best way is to represent it geometrically. So in some sense, here you have the sum of all other qubits. So they live in some hyperplane here, and orthogonal to this hyperplane, you have the direction here, ket k0. Okay? And so here, so this is ket psi h. So this is here, it's very, very close to this hyperplane because the weight is much on this direction than on this one. Okay, so here the angle between this direction and that one is very skewed, and theta here, theta over 2, the angle is very, very small. Okay, so here think of capital N 1,000 or so 1 billion qubit, 1 billion, okay? So the sinus here is very small. Okay, and what does exactly a Grover algorithm? So Grover algorithm helps you to rotate, in some sense, this state to that one using one application of Grover by an angle which will be a theta, and you will be able to do this so many times with always the same theta here, and at some point here you will get so the angle between ket0 and that state will be very small, and here we will observe the state. Okay, so this is the main goal. Okay, so after applying the step L time, so the angle will be here theta L, and it will be more closer to the orthogonal state here. Okay, so here, in order to know exactly how many steps you have to do this, so the first thing you do is that you see that theta over 2 is small. So if the sinus, so if the angle is small, you know that the sine is equal to the angle. Okay, so you know that theta over 2 is about 1 over square root of n. And also you need that at the end, so the angle here will be about L theta, because here is very small. Okay, and at the end, L theta is about pi over 2. And so L will be pi over 2 theta. And if you replace theta by 2 over square root of n, so you will get this value. Okay, so the number of times that you have to apply Grover algorithm, it's square root of n, of order square root of n. Okay, so it's not too complicated. Now I have to compute exactly what is the probability to observe the state at the end. Okay, so the probability to observe ket0 at the end, it will be given, in fact, by square of this sign here. Okay? So in order to compute this, I need to compute, in fact, sine of theta L square. Okay, so I know that theta L is, in fact, close to pi over 2 by some shift by theta over 2. So here I show you the sign, and I show you here pi over 2. And so I know that theta L is, in fact, in this range. So I know that the sinus of theta L will be larger than the sinus of pi minus 2 divided by theta over 2. Okay? So now what is exactly, so I know that the sinus is larger. This sine is, in fact, is equal to this cos. and the cosinus, you can do some Taylor evaluation. You can show that it's larger than this one because the fourth term is positive. Okay, and now you can also observe that in this range here, in fact, the sinus is larger than x divided by 2. In fact, x divided by 2 will be that line here, and that line here is below that one. Okay, so in fact, you can apply this, and I achieve a lower bound, in fact, in this case on 1 over square root of n, and if I apply some small math, I can achieve that, so at the end, the sign of theta L is larger than this value. Okay, so now I can square everything to compute the probability. So there is no need to have some absolute value here, but I don't care. And I can show that this value is smaller than this value. Okay? So this is the probability at the end to observe the correct state that we are looking for. Okay? So now I have to explain you why, in fact, in Grover algorithm, we are doing some rotation. Okay? And this is, in fact, in 2 steps. So the first step is to see that the function that we evaluate, in fact, is this function. In fact, it's always equal to 0 for all value except for k0. Okay? And in this case, so here I put 1. So the state here, in fact, is this one. Okay? And according to this value, I just have to look at what is, in fact, the output here. And the output here, in fact, S, is in fact equal to this value. So if k is equal to k0, so here I will have minus this value, okay? And if k is different from k0, I will have a plus here. So I can rewrite everything just using, in fact, this notation, and I, in fact, factor with this value. So in fact, for all different value at the beginning, so this is the input of the oracle function here, I have the superposition of all value, and at the output, in fact, I will have this superposition. That means that all value is a plus, except for this specific indices, okay? So this is just, in fact, the symmetry by the correct angle. Okay, so just have a sign on the right position. And I just have to imply this symmetry. And to do this, so I see that this is a symmetry according to all of the value here. So the oracle is doing this value. So you see that the sign here is in fact minus k0 here. And all of the value here are unchanged. Okay, so it's a symmetry according to the hyperplane here. Okay, so in order to perform this symmetry, we have to look at what is the unitary matrix representing a symmetry. One easy case is, for instance, if you want to do some symmetry according to the k0 here, the direction here. In fact, the symmetry can be written like this. In fact, it's not too complicated to write this. In fact, you see that here, except, so the matrix of the symmetry by S0 is a very simple matrix. It's just these matrices. So you have -1, you have 1 everywhere, except for the value k0 here. But here, in fact, this symmetry, all value, so all value will be changed except the value k0. And if you apply k0 here, you can see that it will be an eigenvector for this unitary matrix. And if it's something that is orthogonal, in fact, if it is equal to 0, it will be shift to minus the value here. Okay, so the value here is that you have 1 here and -1 everywhere. Okay, so this is easy to see that it's a unitary matrix. And in fact, if I want to have a symmetry according to some other axis, so it's always possible to apply, in fact, Hadamard transform before and after, and then you have in the same situations that doing this symmetry. Okay, so you can implement this using only basic unitary matrices. Okay, so the second thing is that the Grover oracle is in fact the composition of these two functions. So this is a symmetry, this is another symmetry, and in fact, so we compose in fact two axis symmetry. Okay, and the composition of these two axis symmetry, I explain you that it is in fact some rotation. And in fact, to see that in fact it is some rotation, you just see that if I compose two axial symmetry with this axis here, and now with that axis, so this corresponds in fact to a rotation where the center of the rotation is the intersection of these two axes, and the angle is twice as the size of the angle between the two axes. Okay, so that explains you why, in fact, when I apply these two axial symmetry, in fact, at the end, I have a rotation by some axis, by some angle that is twice the size of the input. Okay, so this is how it works. And then to implement so the circuit is just, so this is in fact the implementation of the symmetry of this by this angle. And I just remind you that you have to apply the oracle followed by this symmetry. And so this symmetry is just this short circuit. Okay, so it's possible to implement it efficiently. Okay, so I don't know if I have to stop now, or maybe I will just show you some application. So one of the most important application is that one, is that in order to do Grover algorithm on some block cipher, so you can assume that the block cipher has an n-bit input and a kappa bit input for the key, and the output is also n-bit output. So this is a plain text, and this is the ciphertext. And the size of the keys that we are looking at is kappa bit, and maybe we can assume that kappa is smaller than n, but if it is smaller, it's not a big deal. You can concatenate many output of the function. So the idea now is that so you can so the adversary can always query X and receive the corresponding ciphertext, but assume that he got plain text and ciphertext pair that is called Y, and he wants, in fact, to recover the key K0 that map X to Y. Okay, so usually to do this, we can use what is called brute force. So you exhaust all of the different key, and to exhaust a kappa bit key, so you need, in fact, 2 to the kappa operation. And so the number of one operation is, in fact, a decryption. So you decrypt or you encrypt X, and you see if the output is equal to Y or not. Okay, so this is basically the attack. Okay, using Grover algorithm, in fact, you can do something smarter. In fact, you can implement this function. So for the correct, so the function is equal to 1. So fk0 is equal to 1 if in fact X is mapped to Y, and else is, the function is 0. Okay, and if you apply in fact Grover algorithm, you can do this search in fact in time square root of 2 to the kappa. So it's equal to 2 to the kappa divided by 2. And so the running time of Grover algorithm is half of the time for a classical attack. So for instance, if you use AES key with 128 bit, in fact, you can do this with Grover algorithm in time 2 to the 64. So maybe NIST, in the beginning of the 2000, thinks that 2 to the 64 can be doable in the near future. And so that's the reason why he also proposed to have some keys for RSA using 256-bit keys. Okay, so for RSA, you have two different bit keys. Either you can have 128-bit keys. So if you think that quantum computer will not arrive, you have safe with 128-bit keys. But if you expect that
for
it will...
AES, I guess.
For AES, yeah. And if you assume that it's not the case, you have to use 256-bit keys. Okay? There is some other application, but I think that I will stop here if you have any question.
Question for Piranha? We have a lot of estimation for factoring. We have not equivalent for discrete log,
Yeah.
and in particular for elliptic curves.
Yeah. So the question is, so maybe with elliptic curve, so the key are even shorter than discrete log. So it's a lot of crypto systems use elliptic curve cryptography. And so since the keys are smaller, maybe it will be easier to recover the elliptic curve discrete log. And however, currently it's still hard to do this because the implementation, in fact, requires to have an efficient modular inversion algorithm. And currently, it costs a lot to compute some modular inverse. And so maybe it's possible to do something. So we are looking at. Yeah, it's a little bit more difficult. And nowadays, we need, in fact, about the same number of qubits to break an elliptic curve crypto system that use only 256 bit than to break RSA with 248 bit. Okay, so we don't gain, in fact, too much trying to break elliptic curve crypto system.
Other question for Piranha? Okay, so we have all to remember that you say that by 2030 we will be able to maybe factorize.
We will see, I think. I hope that maybe in the future 10 years it will happen. I hope. Yeah, as we said, so we are in cryptography, we are transitioning to post-quantum cryptography. And with Ludovic and Pascal Lafourcade, we are currently writing a book on post-quantum cryptography. So if you are interested in post-quantum cryptography, so it's a completely different topic. So maybe I can just encourage you to try to look at the book. Thank you very much.